talked about several different random processes. We've talked about flipping coins, we've talked about rolling dice, we've talked about picking random people. Sometimes you end up with numbers, sometimes you don't. For example, if I flip 3 coins, you don't end up with numbers. You end up with things like heads, tails, tails, not a number. A random variable is a variable that counts or measures something about the outcome of a random process. What we're doing here is we're forcing numbers to happen by counting or measuring something. And for statistics, the main example that we're going to be talking about is picking random people. Say I pick 5 random people. In and of itself, I don't end up with numbers. If I pick 5 random people, I'll just end up with 5 different people. But I can force it to be a number by counting or measuring something. So say I pick 5 random people, and then I count how many people play Wordle. So then I do end up with a number. Or I can also measure people's heights and then find the average height. And I'll also end up with a number. Now, probability distribution is just a way to summarize the random variable. So it's a table that lists all the possible values of x along with their probabilities. And what I have here are 3 tables. So some of these are valid probability distributions and some of these are not. So what are the requirements of a probability distribution? And before I do that, let's talk about how to read this table. The x column is going to list all the possible values of x. And I think the situation I had in mind here is the picking 5 people and then counting how many play Wordle. So you could get 0, right? You could get nobody plays Wordle, all the way up to 5, which would be all 5 people play Wordle. The P of x column, these are probabilities. So there's 0.16 probability. Remember, probability, you can always interpret it as a percent. So move the decimal 2 to the right. That'll be 16%. So that 0.16 means that if I pick 5 random people, there's a 16% chance that none of them play Wordle. So back to what are the requirements of a probability distribution. Let's take a look at the probabilities in this second table. There's 2 things that stand out to me there. These are supposed to be probabilities, and remember, probabilities are always going to be numbers between 0 and 1. I see a 1.18. That's not between 0 and 1. I also see a negative 0.01. That's also not between 0 and 1. So this second table is no good because probabilities need to be between 0 and 1. So that's one requirement. The second requirement is, let's take a look at the first table. Let me add up these probabilities. So 0.16 plus 0.18 plus 0.22 plus 0.10 plus 0.3 plus 0.01. I get 0.97. That's a problem. Why is it a problem? If I add up the probabilities, what should they add up to? All right, if this is a list of everything that could happen, this should be all of the probabilities that could happen. If I add up all the probabilities, I should get 100%, which as a decimal will be 1. So if I add up all the probabilities, I should get 1. So that's the second requirement. The probabilities should always add up to 1. So that's why the first table is no good either. What about this last table? So let's first check the first requirement. Are the probabilities all between 0 and 1? Yes, so that requirement is checked. What about the total? Let's check the total. Zero 0.06 plus 0.58 plus 0.22 plus 0.10 plus 0.03 plus 0.01. Good, I do get 1. So out of these 3 tables, the last one is the only one that is a valid probability distribution. Okay, so now I want to talk about some phrases that we'll encounter over and over again in this unit. And what I want to do is translate these phrases to math symbols to make sure that we all agree what they mean. Let me start with the easiest one, which is the last one. So x is exactly 11. So translated to math symbols would be x is exactly equal to 11. So x is equal to 11. The next easiest one would be this one here that says x is more than 5 or x is greater than 5. So translated to math symbols would be x, the greater than symbol, which is this one, 5. X greater than 5. How about this one? X is fewer than 15 or x is less than 15. So translated would be x, the less than symbol, which is that, 15. And then the 2 remaining ones are the ones that I think are the trickiest, at least it's trickiest for me. The first one here, x is at least 21. So what does at least 21 mean? So what symbol goes in the middle there? The way I usually remember this is you have to be at least 21 to buy alcohol in the US. So what does that mean? You have to be at least 21. So to be at least 21 means you can be 21 or over, right? 21 or over. So it would be greater than or equal to 21. And that's the greater than or equal symbol. So it has a line underneath, which is the equal part. So you can be 21 or over, which differs from the regular greater than symbol. So x greater than 5 means strictly greater than 5, don't include 5. Greater than or equal to 21 means include 21. So 21 or over. The last one here, x is no more than 2. X is at most 2. So what does that mean? And what symbol would go in the middle here? At most 2 means that 2 is the biggest it can be. So another way to say that is 2 or less. So 2 or less, less than or equal to. And so this symbol here differs from that symbol because less than or equal means you include the 2, so 2 or less. Less than 15 means you don't include the 15. You only include the ones that are strictly less than 15. Example 1. The situation we have here is we're picking a random bag of M&Ms, which in and of itself is not a number. To make it a number, we're going to count the number of green M&Ms in the bag. So why do I care about this? Well, 1, I like M&Ms, and 2, I like the green ones. Don't judge. Notice that there's a missing probability. So the first thing we actually have to do is find that missing probability. How do you find this missing probability? Well, what do you know about the probabilities? You know, 1, that they should always be between 0 and 1. And 2, they should add up to what? They should always add up to 1. So find the missing number so that all the probabilities add up to 1. And I think the easiest way to do this is to just add up what you have so far. So add up all of these together with that. So add what you have so far and you get 0.079 plus 0.106 plus 0.382 plus 0.137. And I get 0.704. And then to get the missing number, just do 1 minus that. So 1 minus 0.704. And I get 0.296. So that missing probability is going to be 0.296. And let's check. Add up all these probabilities, make sure it's equal to 1. 0.079 plus 0.106 plus 0.382 plus 0.296 plus 0.137. And it is 1. So we're good. So now let's answer these questions. Part A, what's the probability that a randomly selected fun-sized bag has exactly 5 green M&Ms? Okay, so you're going to see phrases that we talked about on that first page, right? Exactly 5. What does that mean? So in symbols, what we're looking for is the probability of getting x exactly equal to 5. And this is telling me which probabilities I need to add up. So exactly equal to 5 just refers to the 5. So this just refers to the 0.106. Part B. What's the probability that a randomly selected fun-sized bag has more than 6? In symbols, more than 6 is greater than 6. So which x's are greater than 6? Greater than 6, remember, does not include the 6. So we're talking about the 7 and the 8. Okay, 7, 8. So we're going to add up the probabilities for the 7 and the 8, which is 0.296 plus 0.137. So 0.296 plus 0.137. 0.433. Part C. What's the probability that a randomly selected fun-sized bag has no more than 5? No more than 5. What symbol goes there? And if you don't remember, go back to that first page. No more than 5. No more than 2 is x less than or equal to 2, which means no more than 5 is x less than or equal to 5. Which x's are less than or equal to 5? So less than or equal means include the 5. So this is 5 or less. So this would be the 5 and a 4. So 0.106. That's the probability for 5 plus 0.079. That's the probability for the 4. Okay, so together that's going to be 0.106 plus 0.079, 0.185. D. What's the probability that a randomly selected fun-sized bag has at least 5? Okay, at least 5. If you don't remember what that means, look at the table on the front page. At least 21 is greater than or equal to 21, which means at least 5 is greater than or equal to 5. Okay, the equals part means include the 5, so 5 and up. 5 and up would be the 5, the 6, the 7, the 8. So we're going to do 0.106 plus 0.382 plus 0.296 plus 0.137. Okay, add those up. 0.106 plus 0.382 plus 0.296 plus 0.137, 0.921. Part E. What's the probability that a randomly selected fun size bag has at most 6? What does at most 6 mean? I don't remember, so I'm going to go back to my table. At most 2 is a less than or equal to 2. So at most 6 would be an less than or equal to 6. The equals mean include the 6, so less than or equal to 6 would be the 6, the 5, and the 4. So probabilities for 6, 5, and 4 together. So 0.382 plus 0.106 plus 0.079. Okay, add those up. 0.382 plus 0.106 plus 0.079. 0.567. Part F. What's the probability that a randomly selected fun size bag has less than 7? Less than 7 is just going to be the less than symbol. Less than 7, so this symbol, because it doesn't have the equals together with it, means you don't include the 7. So if I don't include the 7, this will be just the 6, the 5, and the 4. So it'll be 0.382 plus 0.106 plus 0.079. And just by coincidence, these are the same 3 numbers that was on part E. So this is just coincidence. So I don't need a calculator because it's just going to be 0.567. Continue with our green M&Ms example. Part G. If a fun size bag is selected at random, how many green M&Ms would you expect to find? Keyword there is the word expect. Anytime you see the word expect, what I'm looking for is the expected value. Which is just another word for the mean. So what this question is asking is, find the mean. So how do you find the mean? Here's the formula for finding the mean. So let's talk about how to use this formula. And so what I'll need here is, I'm going to recreate the table from the previous page. So all I did here was I recopied all the x's and all the probabilities, including the missing one that we found. Because I'm going to need a couple more columns here. This formula is saying, take your x's and multiply by the p of x, which is the probabilities. So it's saying, take each of your x's and multiply by the probability. So I'm going to create a new column where I do exactly that. So the new column is where I take my x's and multiply by the probabilities. Okay, so the first one, 4 times 0.079. .316. So if you get long decimals, round to 3 decimal places. Next one, 5 times 0.106. 0.53. Next one, 6 times 0.382. 2.292. 7 times 0.296. 2.072. 8 times 0.137. 1.096. Okay, so what we've done so far is we've done this part, x times p of x times p of x. We've got a column of numbers. This symbol, which we've seen before, is the summation symbol. That's saying to add up all those numbers. So add up this column. So 0.316 plus 0.53 plus 2.292 plus 2.072 plus 1.096. 6.306. And that's our mean. So the mean is 6.306. So back to part G. It's asking for the expected value. It's asking for the mean. We said we found the mean was 6.306. What's the interpretation here? So the situation is we're taking a bag of M&Ms, we're opening and counting how many green M&Ms. Right? So sometimes you'll get a 4, sometimes you get a 5, sometimes you get 6, sometimes you get 7, sometimes you get 8. If you repeat this process over and over and over again, so take a bag, open it up, count the green M&Ms. Open up another bag, count the green M&Ms. Open up another bag, count the green M&Ms. If you repeat this process over and over and over again, on average, you'll get about 6.306 green M&Ms. Before we move on, let me talk a little bit about where this formula comes from. And before I do that, let me back up a bit and talk about these probabilities. These are probabilities. You can interpret probabilities as percents. Now, back in Unit 1, we also talked about something called the relative frequency, which I also said you can interpret as percents. So you can think of these probabilities as relative frequencies. Now, back when we introduced the mean, we talked about finding the mean when we're given a frequency table. So the way we found it was the frequency table, the frequencies tell us how many of each data value we have in the data set, right? So this 6 means that there are 6 zeros, 11 ones, 7 twos, 4 threes, and so on. And what we did was we listed out the data, the 6 zeros, the 11 ones, the 7 twos, the 4 threes. And then to find the mean, we added up all the data values. And we said that instead of doing 0 plus 0 plus 0 plus 0 6 times, that's the same thing as saying 0 times 6. Instead of adding 1 plus 1 plus 1 plus 1 11 times, that's the same thing as saying 1 times 11. So what we're doing here is we're doing the data value times the frequency. The data value times the frequency. Data value times frequency, data value times the frequency, and then adding it up. Now, what we did here is almost the same thing, right? Instead of doing data value times the frequency, we're doing data value times the relative frequency. Data value times the relative frequency. Data value times the relative frequency, and then adding it up. Now, in the frequency table situation, after we added it up, we divided by the total number of data values, which you can get by adding up all the frequencies, which is what we did here. Now, why didn't we divide here? Well, we kind of are. So if we add up these relative frequencies, what do you get? What do you always get? These are probabilities. When you add up all the probabilities, you should always get 1. And anytime you take a number and divide by 1, you get the same number back. So divide by 1 doesn't change the answer. So that's why we can omit the dividing part in this situation. And that's where the formula comes from. We also have a formula for standard deviation here. Let's find a standard deviation because we'll need it for the next page. So how does this formula work? So first, I'm going to create a new column where I do this part. X minus mu squared times P of X. X is our data value. So this is saying take each of our data value minus the mean, which was the 6.306, square it, and then times it by the probability. Okay. So the first one, take the 4, the data value, minus the mean, which is the 6.306, square it times the probability of the 4, which is 0.079. Okay, let me set up everything and then we'll go back and enter it into the calculator. The next one, our data value is now 5, so 5 minus the mean, which is the 6.306, square it times the probability of the 5, 0.106. Next one, 6 minus the mean, 6.306, square it times the probability of the 6, 0.382. Okay, so be careful. Make sure you're using the probability and not this column, which is x times p of x. So we want the p of x column. Next will be 7 minus the mean, 6.306, square it times the probability of the 7, 0.296. And then finally, 8 minus the mean, 6.306, square it times the probability of the 8, which is 0.137. Okay, so now let's go through and enter all of this in the calculator. So I recommend using the Decimal Scientific Calculator and just enter it exactly like you see it here. So parentheses, 4 minus 6.306, close parentheses, square it. That's the a with a little 2 in the superscript, times 0.079. Okay, these are long decimals, so round to 3 decimal places, 0.420. So in the real world, to be accurate, you would use more decimals, but for this class, let's agree to round everything to 3 decimal places. Okay, next up will be 5 minus 6.306, close parentheses, square it, don't forget the square, times 0.106. And this is 0.181. Next, 6 minus 6.306, close parentheses, square it, times 0.382, 0.036. Next, 7 minus 6.306, close parentheses, square it, times 0.296, 0.143. And finally, 8 minus 6.306, close parentheses, square it, times 0.137, 0.393. Okay, so all we did was we did this part. Okay, we made a column of x minus mu squared times p of x. Next symbol, the summation symbol, that means add up that column. Okay, so we're going to add up this column. 0.420 plus 0.181 plus 0.036 plus 0.143 plus 0.393. 1.173. And then one last thing in the formula. We just did the summation. Last thing is this symbol here, which is square root. So very last thing, we're going to take a square root. Okay, square root of 1.173. So square root symbol, 1.173. Rounded to 3 decimal places, this is 1.083. And that's our standard deviation. Now that we know the mean and standard deviation, we can make the empirical rule picture. And to make the empirical rule picture, remember you put the mean in the middle, and then you use the standard deviation to go up 3 times and down 3 times. And we said that between 1 up, 1 down is 68% of your data, between 2 up, 2 down is 95% of your data, and between 3 up, 3 down is 99.7% of your data. And really, for the purposes of deciding between usual and unusual, I really only need the 2 up, 2 down. Okay, so let me write the 2 up, 2 down. To get to the 2 up, you would add the standard deviation 2 times, right, which is the same thing as saying the mean plus 2 times the standard deviation. To get to the 2 down number, you would start with the mean and subtract the standard deviation 2 times. So that's the mean minus 2 times the standard deviation. And we said that between 2 up, 2 down was 95% of our data. So 95% of the time, you're going to land between 2 up, 2 down. Which means, what percent of the time are you going to land on the outside? So if 95% of the time you're going to land on the inside, what percent of the time are you going to land on the outside? Well, the rest of the percent, right? So 5%. So 5% of the time you're going to land outside of this green area, right? 5% is pretty low, so that means that it's pretty rare that you're going to land on the outside. And something pretty rare, we're going to call that unusual. So if you land on the outside, we call that unusual. If you land on the inside, we call that not unusual. And not unusual is sometimes called usual. So I'm going to use the terms unusual and not unusual. Part H. Would it be unusual if a randomly selected fun size bag had only 4 green M&Ms? So we're back to our green M&Ms example. Would it be unusual if you open up a bag and you got only 4 green M&Ms? Right? I like green M&Ms. If I only got 4, I would be mad. But would this be unusual or not? Okay, so we're going to make this picture. Put the mean in the middle. Our mean was, from the previous page, our mean was 6.306. And then I only need to go 2 up, 2 down, because I only need the 95% range. So 2 up, the way to get that would be the mean plus 2 times the standard deviation. The standard deviation from the previous page was 1.083. Okay, we'll find out later on the calculator. And then I need the 2 down number, which is going to be the mean minus 2 times the standard deviation. And our standard deviation was 1.083. Okay, let's go into the calculator and find these two. The lower one, 6.306 minus 2 times 1.083, 4.14. The upper number, 6.306 plus 2 times 1.083, 8.472. Okay, our mean's in the middle, and these numbers are the 2 up, 2 down numbers. So in between is not unusual. On the outsides are unusuals. And now to answer the question. Would it be unusual if a fun-sized bag only had 4 green M&Ms? So where's 4? Is 4 in the not unusual zone, or is 4 in the unusual zone? Where's 4? Where's 4 on this number line? Here's 4.14. Where's 4? 4 will be to the left of that, which will put it in the unusual zone. So it will be unusual. So if you open up a fun-sized bag and you only have 4 green M&Ms, that's something pretty rare. That's something pretty unusual. And I would be mad. Example 2. A sample of people were asked how many guesses did it take you to solve today's Wordle puzzle. Their responses are summarized below. So in addition to green M&Ms, I also like to play Wordle. Now, in the previous examples, I gave you the probabilities. Here, you have to find the probabilities. So how would you find the probabilities? This example is actually more like what you would encounter in real life. How would you find the probabilities to begin with? You would start by collecting data, by asking people how many times did it take you to solve today's puzzle, and then you would organize it like this and get a frequency table. So this 5 means that there's 5 people who took 1 guess. There's 103 people who took 5 guesses. There's 90 people who took 6 guesses. How would we find the probabilities? Remember, I said you could think of the probabilities as relative frequency. And we know how to find relative frequency. To find a relative frequency, you'll just take each of these frequencies and divide it by the total number of people in the sample. So what's the total number of people in the sample? We can get that by just adding up all the frequencies. So 5 plus 17 plus 25 plus 72 plus 103 plus 90, 312. To get the relative frequencies, you'll take each of the regular frequencies and divide it by the total. So the first one's going to be 5 over 312. And round to 3 decimal places. This is 0.016. Next up will be 17 divided by 312. Divided by 312, 0.054. Next up would be 25 divided by 312, 0.080. Next up would be 72 divided by 312. 0.231. That's rounded to 3 decimal places. Next up will be 103 divided by 312. 0.330. And then finally, it's going to be 90 divided by 312. 0.288. Now, because we round it, when you add these up, you might not get exactly 1, but you'll get something close. Now that we have the probabilities, we can now find the mean and standard deviation the same way we did it on the previous example. That's it for today. Have a great day. See you next time.